Hello everyone and welcome to Applied Mathematics and Calculus tutorials for students and engineers. In this tutorial, we provide a concise introduction to complex numbers. Complex numbers are very important and they are used in a large number of engineering disciplines such as signal processing, control engineering, electrical circuits, and fluid mechanics. On the other hand, from my teaching experience in the higher education, I can tell that students are often struggling with complex numbers and operations on complex numbers. This is especially the case for students studying control engineering and signal processing. In this tutorial, we will, number 1, motivate the need for complex numbers. Number 2, explain what is an imaginary unit. Number 3, state the definition of complex numbers. Number 4, provide a graphical interpretation of complex numbers. Number 5, explain how to perform basic operations on complex numbers. And number 6, define a conjugate of a complex number. And finally, we will do several examples. But before I start with explanations, I would like to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as more than 400 free video tutorials that you can find on my YouTube channel. Consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Okay, first we start with the motivation for introducing complex numbers. Complex numbers are actually not complex to understand. In fact, they are relatively easy to understand, so you should not be afraid of the word complex in the expression complex number. First, let's try to solve a simple quadratic equation having this form. X squared minus 1 is equal to 0. Then, we want to provide the answers to the following questions. How many solutions does this equation have? And what are the solutions? This is a straightforward problem. Since this is a quadratic equation, we will have two solutions. The solutions are computed like this. X squared is equal to 1. From here, we obtain that x12 is equal to plus minus 1. That is, x1 is equal to 1 and x2 is equal to minus 1. Now, let us slightly modify this equation by changing the sign. That is, let's consider this equation. X squared plus 1 is equal to 0. Let's try to solve this equation. Again, we want to provide the answers to the following questions. How many solutions does this equation have, and what are the solutions? Well, since this is a quadratic equation, we should have two solutions. This is correct. And we should obtain two solutions after performing several operations. But wait a second. Can we actually solve this equation by using the knowledge of algebra we learned in the basic courses? Let's try to do that. Start from this equation and then we can write x squared is equal to minus 1. From here, we don't know how to proceed. So how to go from here? How to compute x? Does it look confusing? How can a square of a number be equal to minus 1? Is this completely absurd and illogical? Well, mathematicians have been struggling with this problem for centuries. And today, we don't even recognize that this is a problem. However, in fact, it is. At first glance, to our human mind, it looks like this equation doesn't make sense. The problems with this equation originate from the properties of real numbers. One of the most important properties of real numbers is that their squares are positive numbers. So you cannot take a real number, for example, let us take minus 3.1, and if we take the square of this number, we will obtain some number, for example, z, and this number is always larger than or equal to 0. So keep in mind that this is very important. So the answer to our question can be the following one. This equation doesn't have the solution in the field of real numbers. That is, we cannot find a real number x that will satisfy this equation. And this is completely correct answer. When I say a field of numbers, I'm actually referring to a set of numbers. Consequently, we cannot find a solution in the set of real numbers. So we need to search for a solution in another set of numbers. This equation actually has a solution, however, in the set of complex numbers. The set of complex numbers is usually denoted by C, like this. Before we formally define complex numbers, we first need to introduce the concept of imaginary unit I. The imaginary unit is denoted by I. In some papers or in control engineering literature, you will also see that the imaginary unit is denoted by J. However, in this tutorial, I will use the letter I. Here is the definition, and I will read it aloud. The imaginary unit I is the number whose square is equal to -1. That is, I square is equal to -1. To repeat, we define the imaginary unit as a number that satisfies this equation. Okay, in other words, the imaginary unit I is the solution of the quadratic equation. And let's show that. Simply substitute here I, and we obtain I squared plus 1 is equal to 0, or I squared is equal to 1. And that's precisely the definition of imaginary unit. Over here, you can also observe that the number minus I also satisfies this equation. We can show that by simply doing this. And what happens over here, we can write this equation like this. And we have I squared plus 1 is equal to 0, or I squared is equal to -1. Consequently, our original equation has two solutions. x1 is equal to I, and x2 is equal to -I. Next, let's explain how to compute powers of the imaginary unit. We have I to the power 0 is obviously equal to 1. Then we have, by definition, I squared is equal to -1. Then I to the power 3 is actually I multiplying I squared. And then we know that I squared is -1, so we have -I. And let's compute I to the power 4. I to the power 4 is I squared multiplying I squared. And by definition, we know that this is -1 and this is -1. So we have -1 multiplying -1, and that's equal to 1. Here's one very important property of the imaginary unit. There is a certain repetition once we try to compute the powers of I larger than 4. Let us show that. There is a pattern, keep in mind that. Let's try to compute I to the power 5. Let's see. I to the power 5 is actually equal to I multiplying I to the power 4, and this is actually equal to I, since I to the power 4 is equal to 1. Perfect. How about I to the power 6? Obviously, this is equal to I to the power 2 multiplying I to the power 4, and since I to the power 2 is equal to minus 1 and I to the power 4 is equal to 1, we have that this expression is equal to minus 1. Now observe the pattern. What is happening over here? We have the following. We have that this is actually I. This term is equal to the I to the power 2. Perfect. How about I to the power 7? We obviously have I to the power 3 multiplying I to the power 4. And let's see, from here we have minus I multiplying 1. And this is actually equal to I to the power 3. So you can see the pattern. And finally, let's compute this. I to the power 8 is I to the power 4 multiplying I to the power 4. And this is obviously 1 times 1. And again, here's the pattern. I to the power 4. So obviously, from here, and by performing and trying to compute the powers of I for larger numbers, we will see a pattern. Now that we finally understand the concept of the imaginary unit, let us define the concept of a complex number. Complex numbers are numbers having this form. Z is equal to A plus B multiplying the imaginary unit I. Over here, A and B are real numbers and I is the imaginary unit. And keep in mind that the imaginary unit is actually a complex number also. A is referred to as the real part of the complex number, and B is referred to as the imaginary part of the complex number. Z is the standard notation for complex numbers. However, in signal processing and control engineering, we use S to denote complex numbers. Next, let's explain the notation for real and imaginary parts of complex numbers. As I mentioned previously, we use the letter Z to denote complex numbers. Then, let's again write the complex number in the general form. The notation RE of Z denotes the real part of the complex number Z. And obviously, this part is equal to A. On the other hand, the notation IM of Z denotes the imaginary part of the complex number, and obviously we have that imaginary part is equal to B. Over here you can see a graphical interpretation of complex numbers, and let's sketch this interpretation over here. First, I need to introduce coordinate axis. This horizontal axis will denote the real part of my complex number. The imaginary axis will be used to illustrate and to denote the imaginary parts of complex numbers. Then, we know that a complex number has this form. Z is equal to A plus BI. Obviously, we can represent this complex number as a point in this plane. For example, it can be represented by this point with the coordinates A, B. That is, this part over here is equal to A. On the other hand, This part over here is equal to b. Let me sketch it a little bit nicer. Is equal to b. Perfect. Then, actually, our complex number can also be seen as a vector starting from here and ending here with the projections a and b. Consequently, complex numbers are very similar to vector fields. Keep in mind that. This is actually a polar representation of a complex number that's characterized by the length of this vector, and the length of this vector is denoted like this, and this number is called the modulus, that is, something that looks like an absolute value, and this angle over here, denoted by phi, is called the argument or the phase of the complex number. More about this in my future tutorials. Next, let's learn how to perform operations on complex numbers. First of all, we need to provide the answer to the following question. Given two complex numbers, z1 and z2, when are these two complex numbers equal? For example, if I have a complex number z1 that's equal to a1 plus b1 multiplying I, and then I have z2 that's equal to a2 plus b2 multiplying I need to ask myself the following question. When is z1 is equal to z2? Well, two complex numbers are equal if their real parts are equal and their imaginary parts are equal. That is, we need to have real part of z1 has to be equal to the real part of z2, then imaginary part of z1 has to be equal to the imaginary part of z2. From here we obtain the following. a1 should be equal to a2, since these are the real parts, and b1 should be equal to b2. Next, let's learn how to compute sums of complex numbers. Let z1, a1 plus b1i be the first complex number and z2b equal to a2 plus b2i be equal to the second complex number. When you see something z like this, z1 plus z2, you should interpret it like this. You can simply add these two numbers. You can write a1 plus b1i plus a2 plus b2i. And what happens over here? Well, you take the real parts, this part and this part, and you group them together. So you write a1 plus a2, and then over here you take the imaginary parts and you add them together, and you have b1 plus b2 multiplying I. So what did we conclude over here? We concluded the following. The sum of two complex numbers is obtained by summing their real parts and by summing their imaginary parts separately. Consequently, the real part of the number z1 plus z2 is actually equal to a1 plus a2, and the imaginary part of z1 plus z2 is actually equal to b1 plus b2. The same principle holds true for the difference of complex numbers. That is, when you see something like this, z1 minus z2, you should write first of all the first number, a1 plus b1i, then you do the following. You simply write minus a2 plus b2 times I. And what happens over here? Again, you identify the real parts. The real part over here is minus a2, and the real part here is a1, so you can write a1 minus a2, and let's see what happens for the imaginary parts. You take the imaginary part, here is b1, and over here you'll have minus b2, and this multiplies I, and that's it. Simple as that. So what's the principle? Real part of z1 minus z2 is actually equal to real part of z1 minus real part of z2, and the imaginary part of z1 minus z2 is actually equal to the imaginary part of z1 minus the imaginary part of z2. Next, let's learn how to compute the product of two complex numbers. There is a formula that you can apply, however, don't memorize formulas. Learn how to derive them. And it's very simple. Let's see. So we have z1 multiplying z2. Okay, write z1, a1 plus b1i. Then write z2, a2 plus b2 times I. And then you can perform multiplications. So we have a1 multiplying this whole expression. And you have plus b1i multiplying the same expression. So what I did here, I multiplied this thing by this term, and then this thing by this term. And then you can perform multiplication. We have a1, a2 plus a1, b2i, and let's see what happens over here. Plus, let's see, b1i multiplying a2, that's basically b1, a2i, and let's see what happens over here. b1i multiplying b2i, that's basically b1 multiplying b2 multiplying I squared. And I squared is by the definition minus 1. So you have minus over here, be careful, b1 multiplying b2, and that's it. Okay, so what did we obtain over here? To see the result, we need to group the corresponding term. We need to group the real parts and we need to group the imaginary parts. Let's start with real parts. We have a1, a2, a1, a2. Then over here we have another real part, minus b1, b2, plus, let's see the imaginary parts. Here it is. We have a1, b2, plus b1, a2. And that's it. That's the formula. Over here you can see the formula once more written nicely. a1, a2 minus b1, b2 plus a1, b2 plus b1, a2 multiplying I. Another important concept that we need to introduce is the concept of the conjugate of a complex number. Let z be a complex number defined like this. Z is equal to a plus bi. Then its conjugate is denoted by z bar or z overline and is defined like this. Z bar is equal to a minus bi. In words, the complex number and its conjugate have equal real parts and the imaginary parts have opposite signs. Also, in books and in papers, you might see a bar over a complex number. For example, if you see something like this, a complex number, and then on the top of this complex number, you see a horizontal bar, this should be interpreted as the conjugate of this complex number, and you should write a minus bi. Next, let's do a few examples. Here's the first example. We want to simplify this expression. 2 plus 3 times I multiplying minus 1 plus 2i. Let's see. What do we do over here? First, we will multiply 2 with all the terms over here. Consequently, we will have 2 multiplying minus 1, this term by this term, then plus 2 multiplying 2i, this term by this term, then this term by this term, plus 3i multiplying minus 1, then this term by this term, plus 3i multiplying 2i. Okay, let's simplify this expression. What do we have over here? We have minus 2. What do we have over here? We have 4i. What do we have over here? We have minus 3i. And let's see over here. We have minus, let's see, 3i multiplying 2i should be the following. 3 times 2 is 6. And I multiplying I is minus 1. That's why I placed minus 1 over here. And let's see the result. The result is minus 2, minus 6. We group the real parts, and then we group the imaginary parts. 4 minus 3i, and this is equal to minus 8, right? Minus 2 minus 6 is minus 8 plus I. And that's it. Next, let's calculate this expression. 2 plus I, and then over here we add a horizontal bar multiplying I. This horizontal bar should be interpreted as a conjugate of this complex number. And first of all, we resolve this horizontal bar. We can write 2 minus I multiplying I. And let's see what happens over here. 2 times I is 2i, and over here minus I multiplying I. So we have 2i multiplying over here. We have minus 1, and I times I is minus 1 plus 1. And consequently, the expression is 1 plus 2i. And that's it. Okay, that's all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.